So welcome to the first colloquium of 2022. So it is my great pleasure to introduce Ashwin Vishwanath. So he got his PhD in Princeton in 2001 under the supervision of Duncan Haldane. So that before he got Master of Science at the Indian Institute of Technology in Kanpur. So he was subsequently Pappalardo Fellow at MIT, and since 2004-2008 assistant professor and then associate professor at University of California, Berkeley, and professor in physics at Berkeley since 2012-2016. And since 2016 he moved to assume professorship at Harvard University. So he is AP Sloan Fellow, APS Fellow, Guggenheim Fellowship recipient. So he received Simons Investigator Award, Europhysics Prize, Distinguished Alumni Award from IIT Kanpur. So last year he was elected a member of American Academy of Arts and Sciences. So he is also currently serving as the director of Simons Collaboration Ultra Quantum Method, a member of advisory board at KITP in Santa Barbara. And so there are regular, on regular basis, there are great works, great and creative works by Ashwin appearing, and he'll tell us today from about his recent work from the colloquium titled "From Rydberg Spin Liquids to Non-Abelian Anions in Synthetic Matter." So now I pass the stage to you, Ashwin, and thank you for being with us.
Great, thanks a lot, Igor, and again, apologies for joining a little late. So I'll tell you about some very recent work that we are quite excited about. But of course, most of this, given that it's a colloquium, most of this will be trying to set up a good fraction of it will be trying to set up the background of why we find these states of matter called quantum spin liquids so interesting, and why the recent progress in moving towards a new physical realization is something that we find exciting. At the very end, if I have time, I'll tell you about some further extensions to even more interesting and exotic states of matter called non-Abelian phases with non-Abelian anion excitations. But let's see how far I get. So to kind of highlight one of the very interesting aspects of this field. So I'll be talking about a class of states called intrinsically with intrinsic topological order. I'll try to make that more precise as I go on. And one thing that is kind of astonishing about this area is how many different concepts it brings together, and the different physical systems that are involved. So a lot of my talk will be focused on quantum spin liquids, but the fractional quantum Hall effect, it's an old subject, also is very relevant for this this area. It was the first realization of this intrinsic topological order. Some of the physical aspects that the physical concepts that will emerge have to do with anyons, particles that have statistics that are intermediate between bosons and fermions. The other things that it will also bring together is ideas like long-range quantum entanglement, quantum error correction. So things that are relevant if you want to build a fault-tolerant quantum computer. And finally, we'll also see a very close connection to deconfinement, to deconfined gauge fields. That really turns out to be the most efficient high-level view on understanding intrinsic topological order. So in one slide right here, you have the fields of condensed matter physics, basic foundational ideas from quantum mechanics, ideas from quantum information, entanglement, particle physics, confinement and deconfinement, and finally, somewhat engineering aspect. How do you control errors in quantum computers? Okay, so that's something I'll try to bring out in this talk and talk a little bit about these different aspects as we go along. Okay, so to begin the story, let me start with what is conventional in condensed matter physics to begin with this very influential essay due to Phil Anderson, who passed away slightly over a year back. In this essay, he really highlighted the importance of thinking about science in a way that is a bit more sophisticated than a simple reductionist viewpoint. So the title, of course, is More is Different, and the new phenomena that you can get when you bring many particles together, although you understand the laws governing the individual particles very well. If you actually look carefully at the article, he is really focusing on broken symmetry as the paradigm of this emergence, the emergent properties that you get when you have many particles. And the one that he wanted to focus on was that you could have a symmetry that was present in the dynamical laws. But if you look at the ground state of the system, you look at low energies, that symmetry is spontaneously broken. So that is, of course, a very rich idea, and work by many people has looked into symmetry breaking in condensed matter physics in many other contexts as well. And by now we have a very clear and well-formulated theory of spontaneous symmetry breaking. For example, if you give me a state of matter like a crystal that spontaneously breaks the translation and the rotation symmetry of space, we know exactly how to tell it's a crystal. We have all these tools. For example, you have X-ray scattering. You can go and figure out precisely what way the symmetry of space has been broken by the crystal. There are other cases where the symmetry breaking is a little more subtle. For example, in the Bose-Einstein condensate, there is also an example of symmetry breaking. It's a bit harder to pinpoint the symmetry that is being broken. But again, we know how to measure this symmetry breaking. This is the famous picture of the early Bose-Einstein condensates that revealed the condensate. Another thing that is worth appreciating is that you can use this theory to classify all the different ways in which symmetry breaking may occur. For example, you ask how many different kinds of crystals you could have, different ways of breaking spatial translations. You find that it's 230. These are the 230 space groups. What we know now is that each and every one of these space groups is realized by some mineral in nature. Okay, so everything that is possible, anything that's not forbidden by these basic laws, seem to be realized. And I think that's a fact that's good to keep in mind when we go ahead and think about more exotic states of matter. And finally, this idea of this theory of symmetry breaking is a quantitative theory. It's extreme, has many practical applications. Here's one that I kind of like. This is phase diagram of, I guess, chocolate and malt. If you want to understand how these two components appear in this phase diagram, when they're miscible, when they separate out, this is all of this you can understand by this theory of Landau's theory of symmetry breaking. Okay, so of course, one question that can arise is that all there is to emergence, that many particles put together, leads to symmetry breaking, and that's pretty much it. That itself would have been, has a lot of richness, but interestingly, there are many other forms of emergence. This is just the tip of the iceberg. And in fact, another kind was put forward by Phil Anderson just 1 year after he wrote that influential essay, 1973. He kind of envisioned a new kind of a magnetic state, if you like. So you think of he was thinking of an insulator. So the electrons are nailed down to these lattice sites. They don't move around. They have a spin though. And the question is, what are the spins doing when you cool the system down to very low temperature? Here you have a spin and a half at every site. And here is a conventional state that they could adopt. They could just pick a direction and spontaneously break symmetry. But in some instances, what you realize is that these spins, they like to come pair together. They like to find a neighbor. and together form a spin singlet. So two of these spinor halves come together and form a singlet. And this is very reminiscent of the way in which atoms form chemical bonds and form molecules. Okay, if you look at the H2 molecule, it's really a pair of electrons going into a spin singlet. So these are sometimes called valence bonds, and you have an arrangement of these valence bonds, and they themselves could break the lattice symmetries, and that's called a valence bond crystal. So both of these outcomes, if you like, are symmetry breaking of different kinds. But what Anderson envisioned is, imagine a state where you have these singlets being formed at some higher energy scale. And then as you cool the system down, it does not freeze. It does not pick a particular configuration. Instead, because of the quantum dynamics, the quantum fluctuations, it kind of explores many different configurations of these valence bonds. And that state he proposed was a liquid state. So it's not crystallized. It's not breaking the symmetry. It's a liquid state. That's where the name quantum spin liquid comes. It's quantum because it's really the quantum fluctuations driving this disordering. And another name that came up was resonating valence bond. So kind of making an analogy with benzene, where the double and single bonds resonate. But these resonances occur across the entire system. And we'll see later that this is what gives rise to the long-range entanglement of these states. So at this point, it was a picture that he had, and he proposed this could happen. But we have learned since then that not only is this picture correct conceptually, but even just having this kind of cartoon starting point, you can fill in a lot of the details of the theory describing such a state. Okay, so one connection that was made a few decades later was that there's a close relation between the kind of liquid states that were proposed in 1973 and a very different set of ideas coming from gauge theories. Okay, so to make that connection, a hint at that connection, you can get by simply staring at this picture of these valence bonds. So this is one allowed configuration where the red ovals are a pair of spins that have come together to form a spin singlet. Okay, but for the moment, let's just think of them as some entities. We'll call them dimers, these red ovals. And from every side, you see there's one and only one dimer coming out. Okay, so if you were to think of this red being the presence of an electric field for a moment, and the black lines being no electric field, this is a kind of Gauss law. At every point, there's one and exactly one electric field line being associated with it. Okay, and if you think a little more carefully, this is an unsigned Gauss law. So it's sort of a binary version of electrodynamics where the electric fields are either 0 or 1. Okay, and sometimes it's called a Z2, just the group that corresponds to the binary addition, or a Ising gauge theory. Okay, so you can construct a version of Maxwell's electrodynamics, but in 2 dimensions now, because you're thinking of a plane of these valence bonds, and further where you have this kind of binary restriction on the electric field. Okay, and it turns out this is a perfectly consistent way to generalize electromagnetism. And it turns out you have charges, which are really the defects of these kind of patterns. Let's say there's a bond where, for some reason, there is no dimer. Maybe you pulled out the spin at the site. So there's something that corresponds to the electric charge. And of course, with electromagnetism, if you have electric fields, you also have the magnetic field. And in this particular case, the magnetic field or the magnetic flux is also a binary quantity. So it's either there or it's not there. And if you like, you can think of it as magnetic flux of pi. So if you were to take the electric charge around this magnetic flux, you pick up a minus sign. Okay, there's an Aronoff-Bohm effect, and the Aronoff-Bohm phase is exactly -1. Those are the rules of the game for this very simple form of electromagnetism. Okay, so what Anderson's proposal was, we now know in retrospect, is that under certain conditions, a very simple system of spins with certain interactions could end up giving you these kind of emergent gauge charges and be described effectively by a gauge theory. Okay, and there's another set of ideas that this connects to, I just mentioned that there is a minus sign when you take this electric charge around the magnetic flux. And this relates to the idea of anyons. So if you take one particle around itself or around another particle, go all the way around. If you have conventional particles, like whether they're bosons or fermions, going all the way around will always give you a +1 sign. Of course, if you did exchange for fermions, you'd get the -1, but this really corresponds to two exchange processes. Okay, but you can generalize the notion of bosons and fermions to anyons, where you get a general phase. There's certain restrictions on the phase, but in this particular case, if you take an E and an M excitation, take one around the other, you get a minus sign. So this tells you this is not your ordinary form of matter. It's really something that's related to anyons. And you can get more general phases where the fact that it's intermediate between boson and fermion is completely obvious. Okay, so these are the different connections that relate to the quantum spin liquid. And the next question, there are two questions that arise. One is, how do you realize this system? That's really going to be the meat of this talk. But a separate question you could ask is, if you did realize it, what would that mean? Would it have applications? Could you do things differently if you had such a state of matter? Okay, and yet again, there's another idea proposed by Anderson, this time in the 80s, where he went back to his old idea of spin liquids, and he said that the novel excitations that you can get could actually give you, entirely new kinds of material properties. For example, you could get superconductors that have a very high transition temperature. And of course, these ideas were stimulated by the experimental discovery of the cuprate superconductors, which had a very high transition temperature at that time compared to the earlier examples. And he felt that he needed a radical new theory to account for that. Just to give you a glimpse of this theory, we said that we have these configurations of dimers. You can sort of think of them as closed loops. If you take a reference state, you essentially, any allowed state of those dimers is a closed loop. So you have a vacuum, which is a superposition of all of these closed loops. And sometimes you can make a defect, you can make a line which ends, which is not a closed loop. And at this point, you get this excitation. We call this the E particle, the electric charge, the emergent electric charge particle. And these are the new excitations that you can have in the state of matter. And if you combine that, for example, with the M particle, which is another excitation in this state, that combination is a fermion. So Anderson's idea roughly was that this fermion in the state could combine with the electron and give you an object that carries electric charge, but now the statistics has been changed to that of bosons, and it may be easier to actually condense that object and end up giving you high temperature superconductivity. Okay, so this was the proposal. It's still, despite many years, it's still not really been established if this is a viable route to high temperature superconductivity, but it gives you the idea that once you have these kind of states where all the rules of the game have changed because you have new kinds of excitations, you could get very new and different materials properties. Okay, so that's been a major motivation in the search for quantum spin liquids in magnetic materials. Okay, so more recently, maybe a decade after Anderson's proposal, there was another very different motivation that came up for searching for these kind of states. Okay, and this has to do with building a viable quantum computer. So we all know that it's really these quantum superpositions of bits that are crucial in order to take advantage of the power of quantum computers. And this quantum superposition, the environment interferes with that superposition. It kind of makes this relative phase. It destroys the relative phase because you end up entangling with the environment. So this is sort of very nicely said in this by Scott Aronson. The problem with quantum computers as opposed to classical computers, of course you have errors in both, but in this particular case, your computer is really leaking into the rest of the world, and that's really what decoherence is, and that's what makes this whole program so challenging. Okay, so Alexei Kitaev had this nice idea that if you want to protect your quantum information, you should store it in a way that it's hard for the environment to see the distinction between 0 and 1. Okay, so if you are able to protect it from the environment by encoding it in a non-local fashion, and then you're more likely to be able to preserve your quantum information. Okay, and that's actually the idea of many different approaches to error correction, to quantum error correction. Okay, so to give you a slightly a more intuitive idea of why this may be helpful, how you could protect these kind of quantum superpositions. The idea, of course, being that you use states of different topology to encode your quantum information. And it's very hard to tell the distinction, topological distinction, in a way that is local. So in a way that you could expect the environment to be able to detect. Okay, so just to give you an example, a very hand-waving example, here's a contrast between a regular and a Mobius strip. And if you're a microorganism, let's say you're something that's on the surface, you're an ant walking on the surface of these two different strips, it's very hard for you to tell which of the two you're on. Okay, so that's the analogy of the environment. If this is your quantum bit, this distinction, the environment which is locally acting on it has a hard time telling which of the two states you're in, and thereby it's hard for it to decohere your quantum state. And just to show that graphically, you're on this Mobius strip, and locally, unless you went all the way around, you wouldn't be able to tell the distinction from a regular strip. Okay, so that is sort of the motivation. There's very strong motivation to get these states, to realize them in nature. So how are we doing in that program? Well, there's one very successful realization of topological order. It's not precisely the form that is envisioned by Anderson, but it has been successfully realized, and that occurs in the context of the fractional quantum Hall effect. Okay, so to remind you, this is a system, it's a fairly extreme conditions being employed. You have electrons of a very low density, so it's a semiconductor. It's confined to 2D. You apply a strong magnetic field. You can see the magnetic field over here is of order 10 Tesla. You go to temperatures that are very low. In fact, in this particular case, you have to be below 10 Kelvin. The experimentalists have gone way below. And then it turns out by measuring an electrical transport signature called the Hall conductance, you can establish that you have this fractional quantum Hall state. So, for example, the fraction over here is 1/3. And in that state, the excitations, we understand very well now, is have fractional statistics. They have this kind of anyonic statistics and fractional charge and a bunch of other non-trivial properties, just like was proposed in the context of these quantum spin liquids. Okay, so this is really a very successful realization of topological order. You have a physical system, you go down to very low temperatures, you realize this particular state, and you have a way to measure and tell you're in the state. That's really this fractional Hall conductance. More recently, I didn't have it's not on the slide. People have a more direct measure of the fractional statistics. They can literally tell that your state has particles that have this anyonic character. Okay, so we'd really like to emulate this kind of success for the quantum spin liquid states that I talked about before. For one reason is that it's a different kind of topological order. It is not, the details are quite different from the fractional quantum Hall state. The second is that you don't need to apply very strong fields and so on. You'd like to take a material, just cool it down, and there is your topological order. Okay, so to make it more accessible, that's sort of the idea. So of course, over the years, people have been looking for this in various materials. This is the Kagome lattice. So you could have spins on the Kagome lattice forming these valence bonds. But what you find is often the valence bonds either freeze up like this, or they order. This is slightly different. This is a different lattice, but it ends up having this kind of magnetic order. And this sort of resonating state has been hard to find. Okay, so I should say there are a few candidates that are very promising. This is one. It goes under the name of Herbert-Smithite, and a lot of the experiments seem to be consistent with spin liquid behavior. But really nailing down this physics has been challenging. I'll kind of mention a little bit about that later. But ultimately, I would say that at this point, there is no material that we can confidently claim it realizes this vision of the resonating valence bond quantum spin liquid. Okay, so that really is a major goal. So to quote Matthew Fisher, this is already a decade back. The fact that we have not been able to unambiguously identify this topologically ordered phase in any real material outside of the quantum Hall effect, it's kind of like egg on the face for the theoretical community. Yeah, and so it may seem maybe the efforts are one should make more efforts, but there are some intrinsic problems, and I think really identifying the intrinsic problems and addressing them, that's where one will end up making some progress towards realizing these states of matter. Okay, so maybe I'll just pause for a second over here if anyone has questions before I tell you how we plan to go about engineering a system that realizes a quantum spin liquid. Maybe I'll just pause for a second if anyone has a question. Okay, no questions. Yeah, so let me continue. So if you look back at how progress was made in identifying symmetry breaking states and symmetry breaking orders, the key was that you had a way to diagnose the state. If you got a symmetry breaking state, you had a way to tell that you had it. Yeah, and in the context of topological order, we really want a way to tell, if you have the state. Of course, engineering the state is also a second challenge. But if you have the state, you want a way, a positive signature that tells you that you've realized your quantum spin liquid. So currently, what people do is they try to see that there is no other order, and in certain situations, you can prove that excluding all the other options implies that you have to have some kind of quantum spin liquid. Okay, so in the fractional quantum Hall systems, just the quantized conductance is a smoking gun signature that you've realized topological order. The minute you get a fraction, you know that you must have realized a topological order. But what if you don't have that at your disposal? What if you're looking at a spin liquid? Sometimes you also have edge states and non-trivial quantized conductances, but they're not in the electrical channel. They're in the spin channel or in the thermal channel, which are much harder to measure. Okay, and then you need new platforms that are versatile, that you can move around and tune the interactions. If these are rare states, okay, then you won't have access to a bigger range of parameters. So we were really looking for platforms that are extremely flexible and where you have new ways of doing measurement. And of course, if you could do all of this, then you have a hope for applications like we talked about before. Okay, so this is where these Rydberg atom arrays come in. So these are systems that I won't talk about the experimental details here, but just give you a sense for why these are kind of a promising system to engineer new states of matter. So these are atoms that are essentially confined to the sides of a lattice. And you can see that this is of order a micron scale. So they're quite far apart as far as atoms go. And you can make this kind of perfect lattice. And then at each site, you can think of having a spin or a qubit, if you like. There are two states, 0 or 1. And the two states correspond to these atoms either being in their ground state or in an excited state. And so this is an excited, this is a principal number n excited state of the rubidium atom, and this is the ground state. Now, what really makes this whole thing work is that you excite it to a very high excited state. That's why it's called a Rydberg state. For example, it would be quantum number 70. And so the size of this orbit is 70 squared compared to the atomic scale, and that's why you end up getting interactions across these separations that are of order micron. Okay, and so people have realized that they can trap atoms in this lattice, and they can excite them. So you have, if you just look at one of those sites, you have a quantum bit, and you can control this quantum bit. Okay, you can by shining lasers, you can go between the ground and excited state, and you can essentially realize this Hamiltonian, the Hamiltonian of a spin in an effective magnetic field. This is the Rabi frequency that gives you a ground to excited state transfer at that frequency, and this is a detuning. That's like a application of a Zeeman field along the z direction. Okay, so you have your quantum bit and you can control it. But what is really interesting about the system is that there are interactions between the quantum bits. Okay, so there is around each atom there is you can draw a circle, you can draw a radius, which is called the Rydberg radius. And if you excite one atom within this circle, you cannot excite any of the others, although you have this laser on and it's shining and it's trying to make this transition. Okay, so it's really the interaction between these atoms that blocks transfer of ground state atoms into the excited state in the presence of one excited atom within the steric radius. Okay, so this model really has a very simple form. It has the single quantum bit form, but with the additional provision that before you excite an atom into its excited state, you've got to go and check that all the neighboring atoms within this radius are in their ground state. Okay, so that's really the specification of the model. And this degree of interaction, it's very strong interaction. This is precisely what you need in order to make interesting quantum states. Okay, so this model is really defined not just by these parameters, the omega and delta, but also by this Rydberg radius. You've got to choose a Rydberg radius that you can control, and by the spacing of this lattice. Okay, so the question once this platform came on, the question that we wanted to engage with is, can you actually realize a quantum spin liquid with these kind of interactions, completely different from what people had been doing before in magnetic materials, where you have a different kind of interaction, a very different kind of interaction. Yes, so the key is that you go from the kind of picture I talked about before, where spins form valence bonds first, and then those valence bonds resonate. That's a two-step process. You can eliminate the first step by substituting these valence bonds. Instead of thinking of them as pairs of spins, simply think of them as being some quantum bit on this edge that can either be in the ground or excited state. Okay, so if it's in the ground state, we'll say that there is no dimer. And if it's in the excited state, we'll say that there's a dimer on that particular bond. So given that this is on the midpoints of these bonds, any state of this quantum bit over here, or this quantum system, can be associated with the configuration of the bond. Okay, so that simplification, that's called a dimer model, that simplification allows you to make progress, so you don't need this intermediate step of forming the spin singlets. Okay, and there are other models that people have thought about where, for example, this is a model introduced by Kitaev called the toric code, where again, you can get the same state of matter, this quantum spin liquid kind of state of matter, and it's soluble, so you know the state exists. But the price you pay is that you have these further many body interactions. In this particular case, you have product of 4 Z's, the 4 sigma Z's present in the Hamiltonian, which of course is hard to realize directly, but conceptually this model is very useful, and we'll kind of reference it as we go along. So the progress in this field has been going from this truly microscopic model to these effective models that people have been able to solve theoretically and show that you have these quantum spin liquid states. Okay, but then the question becomes, how do you realize these effective models? This one is really challenging. It's got multi-spin interactions, but we felt that these dimer models are a target that we can aim for. And as I'll show you, they're particularly natural with the kind of Rydberg interactions that I talked about. Okay, so our challenge was that we wanted to take this dimer description. A part of this dimer, some of these models that have dimer description, a subset have the quantum spin liquid phase. Those are the situations where you don't freeze the dimers, they actually keep resonating. And we want to know how this overlaps with the set of Hamiltonians that you can get by thinking about Rydberg atoms on different lattices. So one of the major advantages of this system is that you can choose your lattice. It's something that is not, you don't have to appeal to chemistry or solid state crystallography to get a particular lattice. You engineer the lattice by putting down your optical tweezers at certain positions in the plane. So you have this option, and the question is, do you have enough freedom to overlap with these Hamiltonians that have spin liquids? Okay, so you need these two steps. You need to first get the dimer description of the Hilbert space, where you have this kind of constrained Hilbert space. And then you need enough quantum fluctuations that you end up in a liquid state. You don't just freeze up in some particular configuration of the dimers. So it turns out even step one is kind of non-trivial. You take the most obvious lattices, like a square lattice, and think about a circle centered at the center of this site. You don't really end up getting a dimer model. You get something else. This does not really define a Gauss law, if you like. It has some other strange constraint that doesn't really get you into this interesting space corresponding to the quantum spin liquids. Maybe it's interesting in some other ways, but not the way that we are interested in. The one exception we found where everything seems to work out beautifully was for this particular lattice. It's called a Kagame lattice, but the important thing is that you put the atoms, the Rydberg atoms, not on the sides of the Kagame, but on the midpoints of the bonds. Okay, so when you do that, and if you just draw this circle, you find that for this particular radius of blockade, the allowed states are precisely the dimer state that you would be interested in if you want to define the right dimer Hilbert space, which has the spin liquid associated with the spin liquid. Okay, so that was the first promising sign. We could identify a certain configuration lattice and a certain Rydberg radius where you precisely get this dimer constraint. Okay, so you're still not done because unfortunately, when you end up in this kind of very constrained space, it's hard for these dimers to move around, to fluctuate, and very often you end up with a ordered state that's not particularly interesting. Okay, so in order to tell if this melts, you have to do numerical calculations. Okay, and by the way, this lattice, it took us a while to figure out what this lattice is called. It's called the Ruby lattice, and of course you can deform it. It doesn't have to be exactly at these positions. They can be moved back and forth. So that gives you another experimentally relevant parameter, if you like. You could tune that radius. Okay, so this model was examined by doing density matrix renormalization group by Ruben, who's a postdoc at Harvard. And he found, actually, I was a bit pessimistic. I kind of expected that you would have simply these ordered states, but he noticed that, in fact, as you tune this parameter in this model, I won't go into too many details, you can tune from a completely trivial phase to a phase that has this crystalline order. Those are the two extremes in this model. But in between, you pass through a phase that is there is no obvious crystalline order, but yet there is a phase transition from going from the trivial phase. Okay, the trivial phase is something where you can just specify what each of the atoms are doing individually. You go from here to there. The excited state density doesn't really change much, but yet there is a clear phase transition. And that's a sign that we've entered a new kind of state. And we were able to characterize this numerically and show beyond any reasonable doubt that it is indeed the quantum spin liquid phase that we were looking for. Okay, so that was step one. We found a model that has the state. But of course, the second big question that's still left unanswered is, how do you tell? So let's say the experimentalists were to create the state. How would they be able to tell that they had realized a quantum spin liquid? Again, really, this is a question of trying to, it's a very fundamental question because it's trying to answer the analog of the following well-known fact. If you had a condensate, if you had symmetry breaking, you have a condensate of particles, it's very easy to tell what the order parameter is, or the fact that you have this condensate. For example, this was the first imaging of the Bose-Einstein condensate, which is a condensate of particles. So here, what we have is not a condensate of particles, the topological order that we're interested in, or the quantum spin liquid. Instead, it's a condensate of loops. Okay, and you can think of these dimers forming closed loops, and you have all possible superpositions of them. That's kind of the picture over here. This is a sort of an artist's rendering of this condensate of loops. And what we really need to do is to generalize the measurement-based tools for particle condensates to these loop condensates. And if we're successful in doing that, we'll have the tools to tell that we have realized this quantum spin liquid phase. Okay, so I won't go into too many details, but it turns out that this is a fairly tricky problem. How do you tell that you have this loop condensate? It's related very closely to questions in gauge theories, lattice gauge theories. How do you tell if a particular phase of the lattice gauge theory is actually confined or deconfined? There's an early attempt due to Wilson where he defined this loop operator. It's a product of these Pauli operators around a loop. And you ask how these things scale. Do they have they decay as the loop becomes bigger, but do they decay exponentially with the perimeter of the loop or with the area? Okay, and it turns out you can use that to distinguish two kinds of phases, the area and the perimeter law phases. And that can distinguish for you an ordered phase essentially up here and this quantum spin liquid or this topologically ordered phase. Okay, well, it turns out that only works if you're along a certain axis of this phase diagram. Okay, it's when you have so-called pure gauge theories. In our language, it corresponds to having these diamond configurations with absolutely no defects. Okay, in reality, you don't have that luxury. You have to, you kind of cross this phase boundary somewhere else. And it turns out the simple diagnostic does not work anymore. Okay, so you need to be more sophisticated to actually tell that you've realized a quantum spin liquid versus one of these trivial phases. And people have proposed other measures. For example, there's a proposal by Edgerton back in the 80s. If you were to put the system on a non-trivial topology, like a torus, for example, with periodic boundary conditions, you would find degenerate ground states. You could look directly for the excitations and show that there are anyons. There are other things called modular matrices that you could do. There's something known as topological entanglement entropy, very beautiful idea, where you measure the entanglement entropy of different subregions and then make a very careful cancellation between them and then reveal that there is a constant which is not possible in a trivial phase. Okay, so there are all these ideas, but they're all extremely challenging to implement experimentally. They're sort of theoretical notions that make this distinction sharp. So in that sense, they're very useful. Or you can implement them in numerics, but it's hard to imagine implementing any of these in an experiment. Okay, at least that's what I used to say, like till about a month back. And there was this beautiful experiment due to the Google group, where they actually measured the topological entanglement entropy, albeit on a small size system. They were able to do that. So some of these things which we think of as being very challenging to do can, maybe on present day quantum devices, they're kind of becoming a reality. Okay, but at least for our purposes, none of these quite works for these kind of Rydberg atom arrays. So instead, we came up with a different idea. And the idea is really to compare certain loops, very similar to these Wilson loops that I mentioned, where you take a product of all the Pauli operators around a loop. The expectation value of this loop is expected to go to 0. And the way it goes to 0 is not going to tell you which phase you're in. It's always in what's called the perimeter law phase. But then you compare it against the open loop. You make an open string and compare how this decays versus the closed loop. And if you see that there's a distinction, for example, if you take two of them having the same length, but you find that this open loop goes to 0 much more rapidly than the closed loop, then you know that there's some kind of topological distinction between these two. It's somehow sensitive to the ends. And it turns out that this is really a property of being in the quantum spin liquid phase, that when the open loops decay much more rapidly than the closed ones, that's a smoking gun signature that you're in this quantum spin liquid. Okay, and that's really what we used. It goes under the name of the Friedenhagen-Marcoux order parameter. There's a way to make this more rigorous. You kind of do the expectation value of the open loop, take the square root of the closed loop, which has twice the length, and see if this ratio goes to 0. And when it goes to 0, you know you're in this quantum spin liquid phase. Okay, so this gives you a way, if you were to do the experiments, you could define a loop. So the way they do the experiment is that they create their array of atoms. They change parameters to go to the parameter regime where you want. and then finally take a snapshot of the final state. They can tell you which atoms are in the excited state, which ones are in the ground state. And you do it many times, so you collect statistics. So from those statistics, you can evaluate the expectation value of these operators, at least the ones that are diagonal in the same basis as where you do the measurement. Okay, so at least one of these loop operators you can directly measure. It turns out that's not enough to completely characterize the quantum spin liquid. There's an off-diagonal string operator as well that you need to measure, something that is, for example, in the sigma X basis. We'll come back to that. It turns out conceptually that it's extremely important to be able to measure both of them, but this one is really challenging. And this was one of the things that really held us up for a while. Before we could go to the experimentalists, we'd have to figure out a way to measure these string operators that their action, if you imagine the string operator running along an edge, their action is to really take one configuration and change the diagonal configuration to this one. So something that is off diagonal in the basis of ground and excited states of the Rydbergs. How do you measure this operator when all you have access to is a snapshot of the sigma Z configurations? Okay, so these were the two things we had to do. One is go from our toy model to a realistic model where there are longer range interactions. I won't bore you with those details, but I think this how to measure was really a conceptual, something that is new conceptually. So let me just mention it, partly because it actually works very well, and that kind of came as a surprise. Okay, so this is kind of what the experiment will look like. In fact, I'm showing the experimental data plot. We have a picture of all of the atoms on this lattice. They're created in this so-called Ruby lattice. So this green is the atoms. When the green is excited, we have drawn it with this oval over here. So the oval versus the green is the ground versus the excited state of the atom. Okay, and you can see the many atoms over here. And this is a configuration that you find, and you can see it kind of satisfies this dynamic constraint. So, this site has one and only one excited atom adjacent to this vertex. So you can measure these loop operators that I mentioned, at least in this basis. That's easy. The question is, how do you do it in the other basis? Okay, the off-diagonal strings. And what, again, Ruben figured out was that there's a very counterintuitive way of doing that. What you could do is you could take your system and do a quench. Okay, so you change the parameters in the Hamiltonian suddenly. In fact, what we proposed was to change the Rydberg radius. So you bring in the radius of this blockade by a factor of 2. Then you time evolve for a particular amount of time, this particular amount of time for reasons that are not very obvious. And then you simply measure in the diagonal basis. And when you do that, it turns out you pick it out at this exact time. You find that measuring the loop operators in the diagonal basis after this process is the same as doing it in the off-diagonal basis at the initial time. Okay, so this gives you a dynamical protocol to go and measure both kinds of loops. So then we were finally ready to talk to to approach the experimental team or propose this as a reasonable experiment. And we had a model, we have a set of parameters. Numerics seems to support the kind of state we were talking about. And we had a way to measure, if you were to realize this state, to measure and tell that you're in the spin liquid state. So we worked with this amazing group of experimentalists headed by Misha Lukin. And just a few months after this proposal came out, they were able to implement this. I think it's a testament to how versatile this platform is as well. Show signs that this kind of physics is appearing in these systems. So I won't go into too many details of the experiment. You should really invite one of the experimentalists to talk about this. But roughly speaking, to kind of make the correspondence, to give you a kind of appetizer for how the theory ended up connecting with the experiment, these loops could be measured, and the way in which the experiment is done you start with a very trivial state, and then you adiabatically evolve it into the regime that you're interested in. Okay, and then you go and measure these kind of snapshots. And in fact, you do see that you're entering the dimer subspace. That's really what these graphs show, that when you take a loop, you get exactly the right sign that you would expect if you're entering the dimer subspace. Okay, and then you can also measure the off-diagonal loop using this dynamic loop trick that I talked about, and that seems to also have a promising signature. And then finally, you can do this ratio, the thing that really, when it's small, really tells you that you're in this spin liquid phase. Okay, and so again, I won't go into too many details, but we can simulate this whole system, this whole process dynamically, and the numerical simulations agree fairly well with the experiment, at least the overall trends, although some of the, as you can see, the experiment, as you would expect, has smaller coherence than the numerics. But you see roughly the same kind of trends. So we really believe we know what is happening in this particular experiment. Okay, so Igor, actually, let me pause over here. How much time do I have left?
Right, yeah, if you could maybe just a few minutes so that we have time for questions. So now we've been...
Okay, yeah. Yeah, so maybe I'll just leave you with a teaser about some of the very recent stuff that we have been thinking about. So this is really trying to improve on the previous preparation, which is so what happens there, as I said, is you start in a very trivial state. So in the space diagram, it's some particular value of this ratio where the state is kind of obvious. And then you change parameters adiabatically and move to the part of the phase diagram that you're interested in, the spin liquid phase. That's how the experiment is done. Now, of course, you have to do this slowly because you cross a phase transition. Fortunately, this phase transition is a continuous phase transition. So you have to go slower than the gap, and the gap is set by the size of the system, the inverse size of the system. So ultimately, you need a time that grows linearly with the size of the system. Okay, if you can do that, you're likely to be in the ground state of the system. Okay, but as you can see, as you go to bigger and bigger systems, this is getting more and more challenging to do because you have to maintain quantum coherence over this longer period of time. And in general, you can make this argument when you want to make these non-trivial states like the quantum spin liquid, starting from some very trivial state, which is just independent states of quantum bits. The number of quantum gates you need to apply grows linearly with the size of the system. So in fact, some notion of time grows linearly with the size of the system. So what we have been doing recently is trying to figure out how to get around this barrier, how to prepare these non-trivial quantum states fast in a way that is independent of the system size. Okay, and it turns out you can do that if you allow for measurements. So just to end with one, just to highlight this idea, there's we can appeal to popular culture where this is what we really want. We want a fast preparation, maybe not furious, but a fast preparation. And there is something that is dual to this, these movies in popular culture, which you may be less familiar with, but I did find this on a Google search, something that's slow and measured, but what we really want is some combination of these. Okay, so we can do fast preparation of these non-trivial states if you do measurements. Okay, so I won't go into the details of that because I'm running out of time, but if people are interested, feel free to ask. And one of the interesting things is that you can also get non-Abelian topological phases following that the measurement-based procedure. Okay, and that's something that we are quite excited about. Okay, so let me just summarize over here. The synthetic platforms, they really give you powerful new tools to generate exotic quantum states, very flexible, they're tunable, and maybe equally importantly, you can access non-local correlations like these loops and strings, and that was key for us for being able to establish this kind of topological order. And there are many open questions. The dynamics is very interesting over here. You go from a confined to a deconfined phase. It's really the dynamics of deconfinement it's poorly understood, and also these measurement-based protocols. I think there's a lot of theoretical meat, and of course, also implementing them in real systems seems to be a real possibility at this point. So let me stop over here And thanks for your attention.
Great. Thanks, Ashwin, for this very informative talk with beautiful results.